In this video, we solve problem number 4 from the fall 2020 quiz number 8 in our elementary differential equations class. We're given a system of first order differential equations subject to initial conditions, and we're asked to solve with the Laplace transformation. We always start by letting the Laplace transform of x of t be big X of s, and the Laplace transform of y of t is big Y of s, and then we take the Laplace transform of each of these equations. Of course, we're talking about taking the Laplace transform of the left-hand side of the equation and the right-hand side of the equation. The Laplace transform is a linear operator, so you can just apply it to each of the terms separately. So we get s times big X of s minus little x at 0 plus 3 times, the Laplace transform of x is x of s, plus the Laplace transform of y prime, which is s times y of s, minus little y at 0, equals the Laplace transform of 1, which is 1 over s. Now, our initial conditions told us that x of 0 is equal to 0 and y of 0 is equal to 0. So if I'm trying to write this as a function of s times x, I can write it this way, plus a function of s times y equals a function of s. I just have to factor out that x of s from these two terms, and I get this. Okay, now let's do the same thing with the second differential equation. The Laplace transform of the left-hand side is Laplace transform of x prime minus the Laplace transform of x plus the Laplace transform of y prime minus the Laplace transform of y, and that equals the Laplace transform of e to the t. Okay, that's s times big X of s minus little x at 0 minus big X of s plus Laplace transform of y prime. So that's s times y of s minus little y at 0 minus big Y of s equals the Laplace transform of e to the at, where a is equal to 1, and that's 1 over s minus a. So that's 1 over s minus 1 in this case. Our initial conditions are that x of 0 equals 0 and y of 0 equals 0. So we have this s minus 1 times x of s plus s minus 1 times y of s equals 1 over s minus 1. Now you could use this equation if you wanted to, but I probably wouldn't. I think I would divide both sides by that s minus 1. So this is equivalent to x of s plus y of s equals 1 over s minus 1 times 1 over s minus 1, which is s minus 1 over s minus 1 squared. Now I have a system of two equations and two unknowns. There are lots of ways to solve this system. You could solve by elimination. You could solve using the addition method from pre-calculus or college algebra. Either one of those would be fine. But we're going to solve using Cramer's rule. So we know that this is equivalent to this matrix form. According to Cramer's rule, x of s is the ratio of these two determinants, provided that the determinant in the denominator is non-zero. That just means this system of two equations and two unknowns only has one solution. It doesn't have infinitely many solutions or no solutions. The determinant of this is definitely non-zero. These two rows are not multiples of each other, so they're linearly independent. Now up here, we're going to have exactly the same determinant, except you replace the first column with this column over here. So we still have an s and a 1 here, but in this column we'll have a 1 over s and a 1 over s minus 1 squared. So we'll multiply across this diagonal, multiply across that diagonal, and subtract. In the denominator, we have this times this, minus this times this. That's nice. So just dividing by 3. So we end up with a 1 over 3 times 1 over s minus s over s minus 1 squared. Now that I don't have a transform for, but I can just use algebraic manipulation to get x of s into a form such that I can use my rules for computing an inverse transform so that I can use my table. I really want that numerator to be an s minus 1. Because if it were an s minus 1, then I could reduce it with this s minus 1 squared in the denominator. So I'll just subtract 1 to make it what I want it to be, and then I will compensate by adding 1. Isn't that nice? And that just leaves us with 1/3 times 1 over s minus this over this. So one of those will reduce, and I just end up with a 1 over s minus 1. Then I'm subtracting a positive 1, so that's subtracting 1 over s minus 1 squared. And that is very easy to compute the inverse transform of. So I have 1/3 times the inverse transform of 1 over s, which is 1, minus the inverse transform of 1 over s minus a, where a equals 1. That's e to the at, so it's going to be e to the 1 times t. And this is 1 over s minus a squared, where a equals 1. And that turns out to be a t times e to the at. So that is our x of t. Now we can go back to the differential equations and see if there's any easy way to find y. Well, we could just plug in x prime here and x here, and then use this differential equation to find y. Let's do that, rather than using Cramer's rule again. Although it really wasn't that bad, was it? Actually, I think let's use Cramer's rule again. Although you could use this other method that I'm talking about, it would require a little bit of anti-differentiation. Let's avoid that altogether and just use algebra. According to Cramer's rule, y of s is this. The determinant in the denominator is the same. So you still end up with s plus 3 minus s, which is just 3. This time we leave the first column alone and we replace the second column with 1 over s and 1 over s minus 1 squared. So we have this times this, so that gives us s plus 3 over s minus 1 squared minus 1 over s. And again, we can make that numerator what we want it to be as long as we compensate for whatever it is we're doing. So I've got an s minus 1 squared in the denominator here. I think I'll factor out that 1/3. So I want that to be an s minus 1. So I make that an s minus 1 and I add 1 to compensate. And so we've got this now. So we'll have s minus 1 over s minus 1 squared. That's just going to be 1 over s minus 1 plus 4 over s minus 1 quantity squared minus 1 over s times the 1/3. So y of t is equal to 1/3 times the inverse transform of each of these pieces. That's going to be an e to the at, and that's a 4 times t, e to the t, and that's a 1. I believe that's exactly the same result that we would have gotten if we had substituted x and x prime into this equation, and then we had a differential equation for y prime, and then just took the antiderivative of both sides with respect to t. Once we get that y prime by itself, we'd end up here. We'd end up with this y value. Let's check and make sure that both initial conditions are satisfied. When t equals 0, do we get 0 for x here? I've got 1 minus e to the 0. 1 minus 1 is 0, minus 0. So that's satisfied. And when t equals 0 here, I have e to the 0 plus 0 minus 1. So 1 minus 1 again is 0. So those are satisfied. Now I'm not going to check these differential equations. It's really not that difficult to check. We could check, but I'm not going to check this time. If you want to confirm, you can. But I'm just going to state that my solution is this. My solution is x of t equals 1/3 times this function, and y of t equals 1/3 times this function. And I guess you could think of that as an ordered pair. You could think of those as components in some vector valued function. You can think of it in a lot of ways. I like to think of it as two functions. that together satisfy these differential equations and these initial conditions.